The sun's atmosphere, one of the puzzles that we're trying to figure out is why it's so much hotter than the surface. The core is 30 million degrees and about 10,000 degrees Fahrenheit at the surface. So it cools off like you would expect, like if you had your hands close to a candle, it would just get cooler and cooler. But this is a magical candle. If you go a little bit further out, the temperature shoots back up to millions of degrees, almost as hot as the core. During a flare, during a big explosion in the sun, it gets as hot as the core. We think that this heating, which is what we call the coronal heating, because the corona is the sun's atmosphere, has to do with the sun's magnetic field and its interaction with the boiling motions that occur at the surface of the sun. If you heat gases to millions of degrees, you actually get naturally a solar wind. You get a stream of charged particles that just goes out. And solar wind is continuously streaming out, and we all live in the sun's atmosphere. The Earth plows through the solar wind continuously. And most of the time that's fine, but sometimes we get big explosions in the sun's atmosphere, what we call coronal mass ejections. They're eruptions from the corona into interplanetary space, and they can hit us. The Earth protects us because it has its own magnetic field, and it kind of forms a little bubble for us, but the bubble doesn't work perfectly, and it can lead to very beautiful northern lights when you're up at the poles, but it can also lead to what we call space weather effects. The economic effects of space weather are very significant, estimated to be billions of dollars per year. There's electrical currents that form in space that can disrupt the power grid. There are effects on communications, radio communications. There's effect on our satellites. These particles can hit a chip or a memory on board of a satellite, and the satellite can stop functioning. So there's a lot of negative effects that we are trying to understand better, and ultimately we're trying to predict better so we can protect ourselves better and give advance warning. And for that, we need to understand the fundamental physical processes that lead to all of these events. We have to put satellites into space. And what we do is we take advantage of the properties of light. We split the light into its colors, and we do what we call spectroscopy, where we look at the properties of light, we look at spectral lines, we look at the wavelengths of light. We use the properties of light to say how dense the gas is, how hot it is, what kind of velocities it has, if it's moving towards us or away from us, and how turbulent it is. And as it turns out, that's really key information that we need to figure out the physical processes. MUSE is the mission that I'm leading that we recently started to work on for NASA and hope to launch in 2027. We're really trying to leverage what we've learned about the sun and then also start looking at what triggers these events. There's a lot of questions we have about stellar atmospheres, how they work, how they impact us, and how stars affect exoplanets that may or may not harbor alien life. And so we try to understand and take advantage of our close position to the sun to answer some of these questions.